When scientists use computers to model physics or predict weather, they constantly need to find the area under a curve. But in applied mathematics, exact antiderivatives often do not exist. We are forced to approximate. To solve this reliably, we translate the classical calculus integral into functional analysis. We treat the exact integral as a bounded linear functional, an operator that we will call f. It takes a continuous function from our blue primal space, processes it, and spits out a single real number. We have to know the exact size of this functional to work with it. The norm of this exact integral functional f is simply b minus a, the width of the interval on the x-axis. Because computers cannot calculate the exact continuous integral, we build a sequence of approximate functionals, denoted as fn, to estimate the exact functional f. Abstracting a geometric area into an algebraic functional gives us the mathematical rules needed to guarantee that our computer approximations will not fail when we need them most. Every numerical integration formula is built from two components. First, we select specific points on the x-axis, called nodes. Second, we assign a scaling factor to each node, called a weight. This structure is how classical algorithms operate. The trapezoidal rule and Simpson's rule are just integration methods built around specific, predetermined sets of these nodes and weights. Notice a specific detail about these classical rules. Their weight values are entirely positive numbers. Before we trust these approximations, we must calculate the norm of our approximate functional fn. We need to prove that its norm is exactly equal to the sum of the absolute values of its weights. We prove this by constructing a test function x0 of t with a maximum norm of 1. We design this function so it perfectly flips its signs to match the coefficients. This forces every sum term to become positive, confirming our equation for the norm. Pinning down this exact norm is the only way to measure the stability of an approximation rule as we feed the computer infinitely more nodes. Standard norm convergence fails for these algorithms. The input function x remains completely fixed, but the functional evaluating it is evolving with every added node. To solve this, we rely on weak star convergence. Weak star convergence tracks the pointwise convergence of the sequence of numbers generated when our evolving functionals evaluate that fixed function. The Poliat convergence theorem outlines two requirements to guarantee this convergence for all continuous functions. First, the method must perfectly integrate polynomials. Second, the sum of the absolute weights must be bounded by a constant. The Weierstrass approximation theorem states that polynomials are dense in the space of continuous functions. Combining that density with a bounded norm guarantees weak star convergence across the entire function space. This leads directly to Steklow's theorem. If a method uses only non-negative coefficients, the sum of those weights will always equal the exact integral of the constant 1. As a result, the bounded norm requirement is automatically satisfied. Because Simpson's rule utilizes strictly positive weights, it satisfies Steklow's theorem. This mathematically guarantees the algorithm will converge to the true area without failing. This table maps the three types of convergence used to analyze sequences of operators and functionals. Norm convergence is the strongest condition, measuring direct distance between elements in a space. Weak convergence relies on evaluation by all bounded linear functionals in a dual space. Weak convergence operates specifically in the dual space, analyzing how a sequence of functionals evaluates specific fixed elements from the primal space. These concepts bridge the gap between abstract functional analysis and the physical reality of calculation. They are the rigorous proofs required to validate numerical algorithms. The abstract machinery of Banach spaces and weak star convergence provides the invisible structural skeleton that ensures real-world computing works. If you found this breakdown helpful, subscribe for more step-by-step applied mathematics.